Hypothesis testing is a scientifically sound process, however a limited one. Whereas the hypothesis test will give you a result that the treatment did have a statistically significant effect on your sample mean, you are not able to tell how much the treatment contributed to your outcome. To correct for this, it is recommended that whenever researchers report a statistically significant effect, they also provide a report of the effect size. One of the simplest and most direct methods for measuring effect size is Cohen's d. Cohen, in 1988, recommended that effect size can be standardized by measuring the mean difference in terms of the standard deviation, and created the formula shown on the slide to measure effect size. The table shown right below it is located in Table 8.2 on page 232 of your book. It provides a framework in which you place the Cohen's d value you compute. Typically, you may not compute one of the exact values shown in the table, but you place the value you do compute into the framework of the table. Thus, for example, if you calculate a 0.35 for your Cohen's d, you would interpret it as a small to medium effect size. Finally, researchers also strive to create conditions that will make the research tests be as powerful as possible. The steps a researcher can take to increase the power of the hypothesis test are: 1. Try to compose the largest sample you can. The larger the sample size, the more powerful the test. 2. Increase the alpha level. For example, testing at an alpha of 0.05 instead of an alpha of 0.01 if possible. And 3. Changing from a regular two-tailed test to a one-tailed test, because the critical z-values that form the boundary to the critical region are smaller for a one-tailed test. For example, for an alpha of 0.05, for a two-tailed test, the critical z-value is 1.96. However, for a one-tailed test, it is 1.65. The sample z-test statistic does not have to be as large a value to exceed it.